going to do IPv4 addressing, which is always a bit of an interesting topic. So first thing I'm going to get you guys to do is I'm going to get you to get a file. So let me see if I've got the file ready to go somewhere. Not there. So let's see if we got the files in here. Yep. All right. So there's a whole bunch of files. There's so there's a numbering systems, and then there's a IP subnetting one. Okay. Let me just have a look at let me just copy all of these. So I can't remember which one it is. But get a copy yourself. Okay. So that was in this directory. So when I give you a directory path, oops. And when I give you a directory path, that's something that you need to sort of be able to access. Okay, so that's there. I'm going to copy all the files here, and I'm going to see if they're the appropriate ones, because I can't remember exactly which ones they are. So let's have a look at this one. Yeah, I think this one's the right one. All right, so yep, that's okay. I might just have this on the side, but we might have a blank worksheet on the right. But just get a copy for yourself, okay? And is there anyone just purely online? You are? That's good. That means you won't be able to go to that location. Instead, you can go to the IT Studies NAS. Oops, wrong one, wrong level. Cert 4 level. And there's a NWK4C3 SYN. And I'll just put it right there. Okay, so go to IT Studies NAS to download those if you're online only. Okay, so let's get started with the topic. So if you remember, a couple of weeks ago we talked about numbering systems, and we talked about converting between decimal to binary and binary to decimal. If you remember that. So if you like, I'm going to give you some numbers, okay? So 163. Okay, we'll zoom in a little bit. 163. I want you to convert that to a binary number. Okay, so I'll give you a couple of minutes to see if you can do that. So 163, just convert it to a binary number, because obviously we learned how to do this, and hopefully you still remember. But hopefully, if I just remind you in a second when I go through it, it will jog your memory as well. So go do that while I'm going to go to the toilet for 2 seconds. So I'm going to just lock my screen, but it's 163 for anyone who's online. Jesus, I always find it next to the chat. I thought I was sharing the screen just before. Sorry, guys. I didn't think I stopped sharing my screen. Let's continue. All right, sorry about that. And hopefully, did someone say that? Yeah. Okay. So no, hopefully it's all good. All good now? All right, so we just, so basically we're saying we need to convert this number from a decimal number, which it is, to a binary number. We started off by making a table, and we are doing the values of the columns. Okay, we said that it's a base 2 number, so we go from 2 to the 0 to 2 to the 7, giving us 8 bits being a byte of information. And we said anything to the 0, power 0, is 1. Regardless of if it's a million or a billion or whatever, it's still 1. That's just what it is, okay? And then the following one, to the power 1 is itself. I think that's what you mean, Harrison. Okay, to the power 1 is itself. It's so basically, if you want to make it even easier for yourself, because it's base 2, it's the next column is always double the previous column, isn't it? Remember, base 2, you're timesing it by 2, timesing it by 2. So if I look at that, the previous column is 1, you times it by 2 is 2. The next column is going to be 2 times the previous column, 4, 8, 16, 32, 64, 1 to 8. You guys get me? All right, so if I draw that into a column, meaning that I'll put some borders around it, and I'll put, we'll make that thicker borders, and then I will shade these two a little bit so we can actually make it a little bit different color. We'll make it this powder blue type color because I'm feeling that vibe. Okay, so I'll even center these. Okay, so basically, hopefully you remember that each column, just like in decimal, has a value. Okay, so if we take the decimal numbering system, each one is the ones column, the tens column, the hundreds column, and the thousands column, and so forth. But this is different because it's binary. There's 1s, 2s, 4s, 8s, 16, and whatever columns. So the way we do this conversion is we go right to left, and we ask a simple question. It's binary. It's a yes/no question, isn't it? Okay. The question is, can this number, which is the value of the column, fit into that number? And what's the answer? Yes. Right. So yes equals 1. Okay. So I might make that centered as well. Yes equals 1, and then what happens is that we take that 1 times 128 and put it under here, and we do a minus, and then we actually so we do a minus, enter, and we then draw a line and we work it out. So basically, if we do a line here, and what's the difference? It's 35, is it? Is that correct? Yeah. Okay, good. Someone has to check my work because I'm often not able to do sums in my head while I'm demonstrating. Okay, so now our new number is 35. And we ask the same question for the next column. Can 64 fit into 35? No. So it's going to be 0. Correct. So if we want to be technical, it's 0 times 64 is 0. And if we do a minus again, and we know we're going to end up with 35, aren't we? So literally, we're going to do that. But can you see that I don't need to do that? I'm ending up with the same number, but literally that's exactly what's going to happen. It's the same process, each column, but in this case, I'm taking 0 because 0 times 64 is 0, right? Are you with me, guys? Yep. So I could have done that, but I'm not going to do that anymore because you can see that it doesn't get me anywhere. So I'm just going to skip past it, if you like, if there's a 0. All right, so now the next question is, can 32 fit into 35?
Absolutely.
Yes, so it's 1. So 1 times 32 is 32. And we do a minus like we've been doing. And we put a line above, and we end up with 3. And then finally, we're going to go, not finally, then next we're going to ask, does 16 fit into 3?
Nope.
Nope. Does 8 fit into 3?
Nope.
Nope. Does 4 fit into 3?
Nope.
Does 2 fit into 3?
Absolutely.
Yes. So 1 times 2 is 2. and we do 2 here, we minus here, we get an answer here, which is going to be 1. And then next question, does 1 fit into 1? Yes. And we always, 1 times 1 is 1. And we do a minus. And we always end up with 0 over here before we run out of spaces over here. When we get to this 2 to 0, we should always get to this 0 here. If we don't, then we've done something wrong or the number's too big. Okay, so obviously if I had 256, it wouldn't fit in there at all. So that's too big to fit in a byte. And obviously we would have to go to another column if it wasn't the fact that we're trying to express it in the form of a byte. So far so good? All right, so how about I change this up a little bit? I'll just leave that there, but I'm gonna now I might just delete all of this, and now I'm going to change this number now. We'll delete all of that, and I'm not sure why I inserted the column, but let's start with a new number. Okay, let's start with a new number, 56. Do that. Okay, and hopefully everyone will be able to do it now because I've reminded you how we do these things. And I'll give you like a minute to do it. Okay, you don't have to necessarily draw it on an Excel spreadsheet table or anything like that. You could just do it on a bit of paper if it's faster. 56 is what we want to convert. Okay. Just like 163 was what we wanted to convert last time. All right, so how are we going? Almost there?
That's why you fill in my spreadsheet.
Yeah. All right. All right, hopefully you got that. So let me do it quickly for us again. So same idea. Does it fit? No. Does it fit? No. Does it fit? Yes. 32 here. 24 is remainder. Does it fit? Yes. 16, and then it's 8. And then does it fit? Yes. And it's 8. And then 0, and we've already got to 0, so none of these is going to fit, and that's what the binary number is. Okay? Process is relatively simple as long as you have the understanding. Okay? So hopefully you agree with me on that, but let's continue. I'm going to go around the room and I'm going to ask you yes or no, okay? You got to say yes or no. So, Pavel, yes or no? Yes or no? Yes. Yes. What's it? Navaldi, yes or no? Yes. Harrison?
No.
And Paul? Yes. And Nick? Yes. Yes. Lauren? No. Mohammed?
Yes.
Yes. And online, Jaden? Yes or no? Jaden, are you there? Can you hear me? Okay. Okay, but by the fact that he can't hear me or not there, it's going to be 0. All right, so I just randomly made that binary number, haven't I? Just by going around a room, you could have given me any answer you wanted out of the 2. It's a closed question. And basically now we've got a binary number. Okay, so how do we convert a binary number to a decimal number? It's basically the reverse of what we just did there, but let's just put it into practice. All right, so what I'll get you guys to do, again, I'll give you a couple of minutes. You got this table now. Just a couple of minutes to try to convert this binary number to a decimal number now. Just give it a go. All right, so I've given you 2 minutes, and hopefully you've all got there. But if you haven't, then let's do it. So basically, it's the reverse of what we did before from binary decimal to binary. Now we're going from binary to decimal. What we have to do is instead of actually taking away, we've got to add down. So what we do is we go to each one of these columns and we look at the number here, which is what's in the column, versus the value of the column. The question is, what is 1 times 128? 128, right? Then we go to the next one. What is 1 times 64? 64, I know I should just get it, but instead of taking away, we're going to, instead of taking away, we are going to add. Okay, and we are going to keep on adding. So I'll minus this thing. So we'll clear that. And we're going to keep on adding all of these down. So we'll just all of these, and we'll clear all of these until we need one, I guess. And we might just delete these that we don't need. Okay, so we keep on doing that. So 1 times 68, now 0 times 32 is 0. We add 1 times 16, 16. 1 times 8, 8. 0 times 4, 0. 1 times 2, 2. And 0 times 1, 0. Okay, we'll delete these. We don't need those. And we just put in our sort of line for our working out answer, and we add these numbers together. So I'm going to do in my head. You guys check my answer. 128 plus 64 is 192. Give me a nod if you agree. Plus 16 is, what's it, 192? 208. Yeah. Plus 8 is 216. And plus 2 is 218, right? So obviously we just got rid of the 0. We ignored the 0. Zeros make no difference, right? And hopefully you understand that from a basic math type thing. And obviously, if we wanted to check our answer, we can get our calculator out and we change it to programmer. And we can just basically, we'll clear everything and we'll type in this case, it's a binary number. So we'll type in a binary number 11011 010. And if you look at decimal, that's 218, which is what we got. So if we go change it back to decimal, you can see that we can put in any number, 192, for example, and it'll give us the binary. Okay, so this is a good way of checking. And you probably go, oh, we've got all these calculators and AI. Why do we even need to know how to calculate this? You need the reason why you need to know how to calculate this is because it's not the calculation per se, it's the way we calculate it, and because we're going to look for things, and we're going to use this when we do subnetting. Okay, subnetting. So let's start with an IP address. What is an IP address? Okay, so I've done the IP config command, as you've seen me do plenty of times before. And if you look at this IP address I've got for my Ethernet card, you've seen this probably many times again on my computer. And you can see there's 4 decimal numbers, isn't there? Okay, so this is what's called a dotted decimal notation. It's a decimal number, dot decimal number, dot decimal number, dot decimal number. And accompanying your IP address is always a subnet mask. And obviously in this case I've got a gateway, but we don't technically need a gateway to have an IP address and be on a network, but we've got a gateway. And here I've got another subnet mask, haven't I? Another IP address, another subnet mask on another Ethernet, or in this case, a virtual Ethernet adapter. So, yeah, I'm sure all of you can see, all of you will be able to see that this IP address is on a totally different network to this IP address. You can see that? You can see that because you're human and you can probably recognize patterns. But why? Why can you see that? What's the reason? What's the reasoning that you're telling me that they're on different networks?
Suppose on the network mask is different.
The subnet mask is different.
The numbers of
Yeah, I know what you mean. I just want you to say it, of course, and we're here to learn, so that's why we want to say it clearly. So what Paul is saying is those numbers corresponding with these 255s on the subnet mask in the same areas are different, aren't they? Ooh, remember I was talking about that question in our assignment? So we determine if a IP address is on the same network as us or not by doing what's called a Boolean AND with our IP address and our subnet mask. Okay, because if we just looked at these numbers, it's pretty easy, but we could get, in the future, we could get all sorts of weird numbers, especially if you go on the internet, because the internet, like we said, is running out of IP addresses, so you're not going to get nicely segmented networks with where there's 255.255.255.0, because that effectively means your whole network is going to have 254 hosts, IP addresses. Because on the internet, every IP address is valuable, and some people don't even need 254. Just imagine someone I just need 5 IP addresses because I've got 5 computers that has to be on the internet. Then you just give me a 254 address block. That basically means I'm wasting quite a few of them, aren't I? And we just said they were very valuable. So therefore, there's a need for subnetting. But let's talk about the subnet mask first of all. Okay, let's minimize that. So if we actually, we just paste the numbers there. If we actually convert 255 into a binary number, all right, so this is that's the 218, wasn't it? That was the 218 IP address. Oh, so binary number, and 255 is that it's part of the subnet mask, as you saw. If we converted that into a binary number, remember we asked the question: does 128 fit into 255? And the answer is yes, isn't it? 128, and we minus. Oops, we go and delete all of these first of all. Okay, so it's going to be something 127. Yep. All right. So then, what does 64 fit into 127? Yep. So it's going to be 63. Is that correct? I think so. And does 32 fit into 63? Yes. And 32 minus that, and it's going to be 31, I believe. You notice the answer is always one less than the previous number, isn't it? You're seeing a pattern there, aren't you? Hopefully you are, because the next one fits in as well, and it's going to be 15. Yes, 8 does fit into 15, so we'll put that down, and I'm guessing it's going to be 7, even when I was looking at the, even without looking at the sums, and 4 it's fit into 7, 4 it's going to be 3, and we'll put that negative there just for completion's sake, and then it's definitely 2 is going to fit into there, and definitely it's going to be 1, and definitely 1 fits into 1, which gives us 1 here and a negative sign, and we always get to 0, as I said before. Let's put the right lines under here, just so we can see that a little bit clearly. So this is it. Okay, so I'm going to make this a little bit yellow, different color, should I say? And I'm going to make this a different color. Let's make it green, a green gold. Okay. So can you see that 255 is always equivalent to all the filled columns? Okay, easy enough to understand. Okay, when all the columns are equal to 1, it's 255. Okay, that's kind of easy to remember, isn't it? When all the columns is equal to 0, it's equal to 0, but when all the columns are equal to 1, it's 255. And that's the same in an IP address, isn't it? Okay, so if we do what's called a Boolean AND, a Boolean AND sometimes is referred to as a AND symbol, what we have to do is we have to ask ourselves a question between the IP address and the subnet mask. Okay, so this is the, let's say that's the IP, and that's a subnet mask. So let's just say we've got an IP address of, let's move it here. We've got an IP address of 218.16.82.16. And we'll make this a little bit wider. And the subnet mask, we've got 255.255.255.0. And again, make that a little bit wider. And we're just taking that first octet. And when we say octet, I mean each one of those regions between the dots is 8 bits. Oct means 8. So far, so good? All right. So if we're just taking those ones in red and line them up here, and we do a Boolean AND, we're asking ourselves a question. Are both this number and the number it's sitting above both equal to 1? Yes. And we get a 1. Okay, let's center this as well. And same question here. Is both these two numbers equal to 1? Answer is yes. Same question. Is the both numbers equal to 1? No. Both numbers equal to 1? Yes. Both numbers equal to 1? Yes. Both numbers equal to 1? No. Both numbers equal to 1? Yes. Both numbers equal to 1? No. And basically, after a ANDing process, we are able to get this. Some of you guys who are a little bit smarter will recognize what's happened. What's happened? What's that number equal to? Exactly. That number is exactly the same as this number, isn't it? Right? So basically, that's the official process. The Boolean AND process is doing that. Okay? But reality, if you want to do a shortcut in your head, is if anything is sitting over a 1, it's just going to go straight through, straight through. So therefore, this first octet is going to be equal to 218. Okay, so let's get rid of this now. And this is just more working copy. Obviously, we can do anything we like to this page. Don't need to be too fussy of what we do and what we don't do. So if you like to think of it, when we do a Boolean AND process, after we finish, so if we actually, let's write a line, and we'll make this blue, and we'll put a line across the top. All right. So when we do a Boolean AND between these two numbers, we end up with this one, right? Because like I said, it just slides right through the ones. You can think of these ones as little arrows going right through. Okay, so those binary numbers just dropped right through, and you end up with this, which is exactly that, right? Well, good. So let's keep on going then. What about the next one? If we follow the same process, you notice the next one's also, let's change this color again. We'll change it to, let's keep it a warm, one of these colors. And we'll change this again. We're lining up octet for octet above one another, right? So if we do this, but you notice that that's also 255. Again, all ones. So whatever the 16 is a binary number, which is just 1 here, and the rest of them are 0. It's going to slide right down, isn't it? So that's going to end up to be 16. Get me? And if we do the same again for the next octet, and we'll change this to a greeny number. We change that to a greeny number, and again you notice it's 255. Again, if we take our little shortcut, wherever the number is sitting above the 255 is going to go straight down. if we do this process properly, that's what we're going to end up getting, right? So we can sort of take a shortcut and just do that. And we'll put 82. All right, now this is a little bit different. Now let's take this one, we make this the star of the show, because this is a little bit different, because it's not sitting above 255 now, it's sitting above 0. All right, let's actually take this now. We'll make that 16. We'll make this 0. And how do you get a binary 0 to 0? How do you convert 0 to binary? What's it going to be? All zeros, right? If it is a decimal 0, it's going to be all zeros as a binary number, because it cannot be any other number. You get me? Because when you add them all up, it has to equal to 0, right? If you have any other number in any of these columns, it's not going to add up to 0. Okay, 16 is interesting. 16, I probably should have chosen a better number than 16, but I was just doing it on the fly, making stuff up as I go. I like to keep people on their on the edge of their pants, so with myself. But I realize now, if you convert 16, it could be good, it could be bad, but it's going to be 0, 0, 0, 1, 0, 0, 0, 0. You get me? You agree with me? All agree with me? Because basically these two don't fit. This one doesn't fit, and the only one that does fit is 16, and 16 takes 16 zeroed, so the rest of them has to be 0, right? All right, now if we do delete this, and we've got this last octet now, the last one on here. Okay, we asked that. Remember our question? Are both these two numbers equal to 1? No, right? That's your answer, no. And are those two numbers equal to 1? No. Are those two numbers equal to 1? No. Are those two numbers equal to 1? No. And you can quickly see it's going to be no for all of these, aren't they? So when you actually look at this end result, it's going to be a 0, isn't it? So if your subnet mask is 0 in that octet, it's almost like a block. If the ones are like little arrows and it just drops down, these zeros are like a block and you can't go through. So wherever is up there is all blocked off and you end up with 0. Is that an okay analogy? All right. So what happens is that if it's equal to 0, then this last octet becomes 0. And that is what our network ID is. Network ID. Okay? So what does that mean? What does that mean is that every other computer that has an IP address, so let's say that's PC1 equals 218.16.82.16. That's the IP address, right? And PC1 with subnet mask of maybe I should do it clearly. Maybe I should do it like this. PC1 IP. We'll get this. Sorry, guys. I'm just thinking of better ways to represent this. And we'll make this bigger. And subnet mask is going to be 255.255.255.0. And PC1, we'll put this in a little box. All right, and I like to shade, if you haven't noticed. All right, so let's just copy this, and we'll paste it here, and we'll change this to PC2, and we're going to change this IP address to, well, let's make it 95. All right, so if our network ID that we worked out for PC1, so this is PC1's IP address, right? So now let's Let's just get a network ID. Let's move this down a little bit. And we'll go net ID equals 218.16.82.0. So if you remember, that's what we worked out here. And if we copy this and we put it, here, and we'll do PC2. And if we won't know what the network ID is, but it will make it 165. Okay, 165. And if we change this to 165, and let's say we don't know the network ID, we can do our simple rules of these ones being over 255 drops right down. These ones over 255 drops right down. The 282 over 255 drops right down. And now this one, 165 over 0, that's totally blocked, isn't it? Remember that? Okay, so it's still going to be 0. So therefore, this network ID is actually going to be that. And now, when my computer, if I'm on PC1, when my computer wants to communicate with PC2, it takes its IP address, does and its subnet mask, and do a boolean and get on network ID. It already has done that. It's in memory somewhere already. And it goes and does the same thing with the PC2. And if they end up to being the same network ID, if you see that these two are equal, then they are on the same network. What happens if I change this up a little bit? Let's say instead of 82, we're going to change it to 92. If it was 92, then this, if it's the same situation, if you look at that, 218 is still sitting above the 255, so it drops right down. 16 is sitting over 255, drops right down, but now 92 is over this 255 and drops down here and becomes 92, and this 165 is on over 0 and it's blocked and becomes 0. Now we take the two network IDs, and are they now identical? No. If they're not identical, if the two network IDs are not identical, they are on different networks. And what do we have to use now to communicate with PC2? Sorry? A gateway, which is a what device? Router, correct. So therefore, we know, if I was on PC1 and I want to talk to PC2, and that's the IP address, now I will need to use my router, which is my gateway, to actually make this happen. So if I say good, all right, let's get on with our PowerPoint for a bit because I've been talking. So basically, an IP address, IPv4 IP address, has 4 areas. Okay, each area is a dotted decimal notation. So 192.168.10.10. And each one of these areas can be converted to a binary number. Okay, it's said to be 32-bit hierarchical address. So let's work with the 32-bit first of all. Why do you think it's 32 bits? Yeah. 4 times 8 is 32, right? 8 plus 8 plus 8 plus 8 is 32. That's why it's 32 bits. Okay. Okay. Now hierarchical means there's a hierarchy. Okay. There's different levels, and obviously a bit like, like there's sort of interrelated. And there's so basically what that means is that on this IP address there will be what's called a network portion and a host portion. Okay, network portion is the part that represents the network, as in this is the network for this IP address, and a host portion is the part that is representing this unique host. So we need a subnet mask. Okay, we need a subnet mask. So basically, if we line up our IP address and our subnet mask on top of each other like we did, the parts of the subnet mask, parts of the IP address, which is above these 255s, or ones, to be honest, when we talk binary, and then we do a binary Boolean AND, we notice that, hey, the network portion is those parts which are above the 255, meaning that when we do a Boolean AND, we end up with, when we do a Boolean AND, oops, it doesn't do it for us. When we do a Boolean AND, we end up with 192.168.10.0 based on that subnet mask, okay, as a network ID, meaning the first 3 octets remain the same, but the last octet became 0, didn't it? So what does that mean? That means the first 3 digits of this IP address, not all IP addresses, just this one, is the network portion, and the last octet is the host portion. And I can see that quite easily because the network portion are the parts that's over this 255. Okay, and the network portion is above the parts which are 0. Okay, so that's how it is. That's how it is for this network, this example network. Okay, let's say this is basically when they're doing the Boolean and they are ending up with the IP address. Okay, so when we have a IP address and a subnet mask, we are ending up with a network ID. So in this case, this subnet mask can also be represented with the ID of the /24. Well, why do you think the /24 is 24 and not some other number?
24 bits.
24 bits, yeah. Yeah, so why is that equivalent to that subnet mask? Yeah, tell me, because we want to say it out loud because we want to make sure we understand.
3 times 8 bits.
Yeah, 3 times 8 is 24, isn't it? Pretty obvious. But why? But the key reason is 24 of those bits are equal to 1. In that subnet mask, 24 of the 32 bits are equal to 1, and 8 of those bits are equal to 0. So the remainder is equal to 0. Okay, still adds up to 32 bits. Is that 24 is saying that there's 3 octets of which are all ones, which is 255, 255, 255, and basically left over 1 octet, which is going to be zeros. So do you see how that's read now? Okay, and we might get other numbers besides /24. We might get /16, /8, and in the future we'll be talking about /whatever. All right, so let's keep on going. Okay, so that's the first type. Yeah, so the IP address range can go from the first number being 1, the last number being 254. Okay, so let's sort of work that out binarily. So if the network ID is 0, that can't be used as an IP address, can it? Because that's already used to represent the network. Okay, so if that can't be used to represent the network, then the next number is where, it's a 1, and that equals 1, doesn't it? And this IP address is 1. There's also another special IP address. Let's insert. There's still another IP address that's very important, and that's where all of these ones are equal to 1. All right, and that's going to be equal to what number? You've seen this number before, 255. So that's where it's what's called a broadcast. let's just call it broadcast, too long. So it's going to be 218.216.82.255. We're still talking about this last octet here, okay? We're not talking about these other ones. So we're talking about, so when we're looking at this, we're looking at the last octet here, okay? So they get confused with any other things. We're looking at this. Let's get rid of this colors now, because we're back to just looking at that last one. So because the first three are network portions, the last one is the host portion. But on the host portion, there's the 0, which is going to be the network ID. There's going to be 255, which is going to be the broadcast for that network. So therefore, if we actually, I should have done it this way. So let's change that back to 1. So that's going to be all zeros. Yep. And this broadcast is going to be 255, and that's equivalent to when it's all ones. So if that's the first IP address, what's the last IP address I could use? What's the last IP address I could use? I can tell you, sorry? 254. Okay, let me just write everything else in first of all. 218.16.82. something. The last IP address is one before the subnet mask is one before the broadcast, isn't it? If that's the maximum number it can be based on binary, one before that is going to be 254. Okay, and one before that is basically all of that being 1 except for 1. Okay, we'll always go. So when we take 1 off, we're taking the value of 1 off, that becomes 0. And that becomes 254, which is the last IP address. Are we okay with that? All right, so on every network, there's a network ID, there's a and a subnet mask, and that subnet mask helps us work out which portion. In this case, the first 3 octets are network, and the last octet is host. And if it comes to IP addresses, then the first IP address is one after. So if it's 0 is a network ID plus 1 is 0 plus 1 is 1, isn't it? Okay. And also the broadcast is the very last number when all the octet is, all the host portion is equal to 1s. And basically the one that's the last IP address is 1 before the broadcast. 255 take 1 is 254. Okay. Okay, let's write down a couple of definitions from that. All right, so from that, I'm just going to go to another sheet because this sheet's getting too messy. Okay, so okay, so let's make this a little bit wider. Let's go here, and we'll format. And I want you to write this down. Okay, just scribble it down somewhere on a bit of note paper, whatever. And what I we want to refer to it a little bit later. Network ID. Okay. Network ID. That should be one word. Network ID is where all the host portion bits are equal to 0. Okay, if we check that, if we know that the first 3 octets are network, then last octet is host, and when the last octet is all equal to 0, then that's the network ID, isn't it? Okay, so now the broadcast ID. And let's make this a slightly different color. So write that down as well. So broadcast address is where all the host portion bits are equal to 1. So let's double check that. So we know from this example that our first 3 octets are network and our last octet is the host. And when the last octet is equal to all ones, the bits, they equal to 255, don't they? I know we could have just said 255, but it's not always 255. That's my point. That's why we're writing those definitions down rather than saying it's 255, because it's not always going to be 255. Okay, so the next one is first usable IP is the network ID plus 1. And we'll make that light blue. And that's probably, I'll just zoom in a little bit so you guys can see a bit better. And the last I think I mistyped this. Should be a plus symbol. Plus 1. We'll just bold that. We'll bold that. We'll make this capital. And we'll wrap that as well. Might just paste it here. And we might just glue that as well. So basically, network ID, let's make that green instead. No way. Green instead. And we'll make this broadcast red instead. And these two are blue because they're related to IP addresses. Okay. So all right, here's something else to write down. Sorry, guys, if I'm making you write too much, but it is what it is. We write it because we're going to refer to it later. Okay. Wrap. And we're going to make this blue as well because it's part of the IP addressing system. I don't know why that's extra big. Okay. So hopefully you've written all that down. But let's keep on going. All right. So hopefully this should be a bit of a reminder. There's what's called unicast, broadcast, and multicast that happens on the network. Uni means one, broad means all, multi means many. Okay, so what unicast is where one computer communicates with another computer. So it's one to one. Broadcast is one to all. So if I want to communicate with all computers on the same network, I will broadcast. And if I want to communicate with a group of computers, but not all computers, so many computers in a group, I will use what's called multicast. So if we look at this network, and this is a computer that wants to communicate with the printer, in this case, it sends what's called a unicast. It goes from this computer to the switch, out of the switch port that's connected to the printer, and to the printer. Okay, unicast. One device to another device. If I want to, in this case, I want to, what am I looking for this time? Okay, what I am looking for, which version? Okay, it's sent from the gateway router this time. Okay, it's looking for a specific IP address. It's probably an ARP broadcast. Okay, it's saying I need to find the MAC address of 172.16.4.1. No, that's wrong, isn't it? That IP address is wrong. Okay. Yeah. Okay. Broadcast sending packets to all. Okay, so forget about what it's doing. Basically, broadcast is where one computer, I think it should be, the picture should be reversed, to be honest. Okay, one computer is sending a packet out into the switch port, and then it's going to come out of all the switch ports and go to all other devices because it's a broadcast. Okay, one to all. But what about a multicast? Multicast is, what if I want to just select a group of computers? For example, all of your computers are streaming to my Collaborate right now, aren't you? But it's not all computers in this room, is it? If I wanted to make it that efficient, I could use multicast where I'm sending the same packet to all of your computers which are participating, but not the other computers which are not participating. So it's sending from one computer, but not to all computers, but to a group of computers, which is called a multicast group. All right, so that's a bit of review from what we know from before, but let's look at the type of IP addresses. So first of all, there are what's called private and public IP addresses. You might have heard me mention that before, and I think in my mentioning before, if you remember, I made a sort of a bet. I bet you if you go home and you go connect to your Wi-Fi network and you do an IP config on your device which is connected to that Wi-Fi network, and you did IP config, your IP address will start with a 10 or 172.16 or 192.168, if you remember me saying that. Okay, and the reason for that is because it's actually 3 different ranges which are designated as private IP addresses. Okay, these are private IP addresses, meaning that these IP addresses will never be used on the internet. It's only used on the LAN, local area network. And basically, your ISP routers, as well as any other routers which is configured on the internet, will never route these IP addresses. Not saying they're not routable, because we will route them internally between our LANs, but it's not routable. It's not going to be routed by the internet routers and ISP routers. Why do we need these private IP addresses? Does anyone remember why we need these private IP addresses?
So we don't run out of IP addresses.
We have run out of IP addresses, but why do we need these ones? So we can. Sorry? Yeah, of course, it's all about communication, but why do we need these private IP addresses? Yeah?
Private addresses used for commercial?
No. It's used for everyone that's internal on the LAN. But Harrison is right, though. Harrison's on the right track. What did you say, Paul? Yeah, basically, we've run out of IPv4 public IP addresses, which are the ones that can be routed on the internet. but we are reusing the same private IP addresses on all of our lands. That's why I made that bet, didn't I? So if we're saving all those computers which are behind your router at home, at work, on this commercial property, on every other commercial property, think of all the thousands of IP addresses just needed for this campus. If we're not using the public ones, we are saving the public ones and extending the life because we've already run out of those public IP addresses. So we use something called NAT, Network Address Translation, to translate these private IP addresses to public ones. But the public ones are only given to the device that's connected to the internet, which is your home router. And these networks can be reused over and over again by as many different companies, different homes, different whatevers, over and over again. Do you think when they send you a router from Telstra and it's been configured with an IP address to give you internally, you think that's a different configuration for every router they sent out? Probably not. It's probably the same as that configuration they send out to everyone. Okay? So basically, every one of those Telstra routers that you get as part of your Telstra NBN, you're probably getting the same internal IP address. So that means these are all being reused. And we use NAT to translate from these private to public. So they're the two types of IP addresses, private and public. But as far as these ranges, go, do we need to remember? If you want to work in IT and you want to quickly get to an answer, you probably should. Okay. So basically, anything that starts with 10 is going to be private. You see this /8? What does that mean? Remember we've seen that /24 before. What does /8 mean?
First number is the network ID.
Yeah, network portion, right? So same idea, like we said, we want to be a little bit more correct than that. That's the end result. Yes, the first octet is the network portion, and the rest of them are host portions. But what /8 means? It means 8 bits are used for subnet mask at once. So which means it's always going left to right. So the first octet is going to be 255.0.0, which now if we do our little apply that sort of Boolean in our head, it's going to be 10.0.0 for any network that starts with 10 and has a /8 subnet mask, right? Does everyone get that, why I'm saying that? So let's see if I can actually type on here. So what /8 really means is, what /8 really means is that it's a /8 /8. Why is it not typing? /8. Okay, so because the slash is this secret thing, is equal to 255.0.0.0 as a subnet mask. Okay. Because it's saying that 8 bits of the of the 32 bits are going to be used as going to be equal to 1, which is basically if you go left to right, that's the first 8 bits, and that's what subnet mask you're going to generate. Okay, and if we do our Boolean ANDing like we did, anything that's above the 255 is going to drop straight down. Anything above the zeros is going to be blocked and become zeros. So therefore, what I'm saying is, if we have this, any 10 dot something is going to end up with that network ID. So the range can be 10 dot anything, can't it? Okay, so this one's /12. This is kind of funny. Really, that's kind of funny. So we're going to leave that for quite a little bit. But this one's /16. So what does the subnet mask look like here? What's the subnet mask look like?
25500.
Yeah, exactly. Okay, because we know there's 8 bits per octet, and 2 times 8 is 16. That's why this one's easier than this one, isn't it? Okay, so that basically means anything that starts with 192.168 is going to be a private IP address. But the funny thing is this one. Okay, it's not quite on the border boundaries of the different octets, is it? It's 12. It's somewhere in the middle. So let's actually work that out for us. Okay, it's all mass at the end of the day. So it's all mass. Let's take this and copy it to another sheet again. And because let's take it right here and put in, well, let's zoom in first of all and put it right here. All right. What happened there? Yeah, let's just take this and put it right. Yep. Right here. All right. So when we have /12, it really, yeah, no, I don't want to equal /12. No. Right. Okay. Sorry, it's not letting me do that because it thinks I'm trying to delete 0 by 12. All right, so it's going to be /12, okay? It's basically saying 12 bits is going to be ones, okay? So we know that it's going to be 255, that's 8 bits. Then it's going to be something. Then it's going to be, whoops, 0.0.0, isn't it? The something is sort of happening in the second octet. It's because the first 8 is always going from left to right. The first 8 is all going to be ones, but then the second one is going to be sort of, how many more ones do we need to make 12? 4. Okay, so it's 8 in the first one, then we got 12 in total, so we need 4 more out of the second one, don't we? You get me, guys? So remember what we said? The subnet mask is where all the network bits are equal to 1. So we're saying that if we have a /12, we need 4 more bits which are 1. Guaranteed. These are hard ones, if you want to put it like that. They're hard ones, and they can't be anything besides 1. So really, if we convert this number, so the minimum number, the rest of it can be all zeros as one example. That's the minimum number. So really, if we convert this, so subnet mask is where all the ones, all the host, all the network bits are equal to 1, and all the host bits are equal to 0. Okay, did we write that down? Okay, no, let's write that down. Subnet mask is where all the network bits equal to 1 and host bits are equal to 0. So let's write that down as a definition. And are we following me? I know that people can get lost very quickly when we're talking about this stuff, but so far so good. All right. What about you, Navaldi? I can't really see you. Like, are you writing this down as well when I'm saying write this down? Because if you're not writing it down, then you're probably not doing what I'm telling you to. So let's put that as purple. So if we go back here, so what is our actual network ID? So we just have to convert that into a decimal number, isn't it? So it's 128 plus 64 plus 32 plus 16. So it's 128 plus 64 is 192. Plus 32 is 224. Plus 16 is 240. So really, when we're doing /12, that means 240. Okay, but let's actually, it's saying it's a range, isn't it? So when we say /12, it's 240. But what the first number can be 0, and the last number, let's copy this down, can be all ones, can't it? That's a max. Oh, oops. And so basically, this could be all ones. So that's a broadcast address. So now, if we look at what's possible, and if we ignore all of this, okay, so if we just take the IP address, out of it, so these are part of the subnet mask. So this is so if this is part of the if we just look at the second octet now, not looking at the subnet mask, if these parts are part of the subnet mask, these are network bits, aren't they? Okay, so these are host bits. So I might just change the network bits to red, so that's more than obvious. And now these are host bits, and we'll make them green, so that's hopefully obvious. Oops, wrong way. We'll make them green, and we'll make these green. So really, our IP address can be 0 up to this binary number. So if we work that out, that's what's it? 8 plus 12. Sorry, 8 plus 4 is 12, plus 2, 16, plus 1 is, what's it? 15. And we can have that number. Okay, so let's keep on going. All right, so let's keep on going. So there's also a special number as well. It's called a loopback address. So you might have heard me say that. So 127.0.0.1 is the loopback adapter. What's a loopback adapter? It's basically a special adapter that's for diagnostics. So if you're not sure if your TCP/IP is working properly, you can even ping 127.0.0.1 even if you don't have a network connection. If you don't have a Wi-Fi, you don't have Ethernet, you don't have anything connected, you should still be able to ping that. It's only for diagnostics. And obviously, if I want to refer to myself, I can actually go and put in my address bar. For example, if I want to access a network share and I want to put myself, I can see what shares I've got on my own computer. Okay. So basically, loopback means yourself. You're testing yourself if you've got that connection. Another one is this. Oops. Another one is this 169.254. 169.254 IP address. Have you heard me mention this one? Remember, when I see this one, I will immediately think there's a problem. Okay, so does anyone remember what I called this one? Yeah. If you remember, I've mentioned a PIPA. Okay, automatic private IP addressing. All right, so automatic private addressing. So basically, this is a IP address range that goes from here all the way to there, and it's an IP address range that's not set aside to be private, but Microsoft has actually bought it, and basically they've configured all their operating systems to go look for an IP address. But if they can't get an IP address because there's no DHCP server or anything like that on the network, it will give itself a people IP address. So let's see if we can show you that. So if I go to my probably network, let's go to my let's look at my virtual network adapters. Okay, so that's the easiest one. So if you look at this, I've got that VMnet 2. If we double click on it, I can see I've got an IP address. That's that. And I can see I've got a DHCP server. DHCP is enabled. No. Okay, well, that's funny. It's not. So let's change it. So we'll make it become obtained by IP address. So obtain automatically. So that's what your computer's automatically set to. And if I double click on this now, I should see I've got an IP address and there is a DHCP server. You're probably going, what? This is a virtual network adapter. Why is there a DHCP server on that network? So if you've been learning your VMware workstation, hopefully you've already covered this, but there's a VMware network, virtual network, what's the editor? If we look at that VMnet 2, so let's just put it side by side. It's called VMnet 2 virtual adapter. If we put that side by side, so that's VMnet 2 is this virtual network. And if you look at this, it says DHCP server enabled, and the address range is 192.168.44. something. You notice that that's 44.1, isn't it? That's from that range. And you can see that there's a checkbox here that's grayed out right now that says use DHCP service on this network. So what if we change it? Okay, so what if I do this? So if I go to VMnet 2 and I untick this and I click apply, okay, so it's applying, it's basically turning off the DHCP. You can see that's no longer enabled. And now if I go to this and I go disable, because it's got an IP address already, I just want it to be, I wanted to get another IP address. So I've re-enabled it, so basically restarted the interface. It got rid of the IP address it had, and now it's going to try to get another IP address. And hopefully, the fact that the DHCP server is not working anymore will allow us to see that there's a 169.254 IP address, which is automatically given it to itself. And that's what we are talking about with this special address range, which is called local link address or PIPA. And that's because it's Microsoft operating system. Okay, just remember that. It's Microsoft operating system. All right, so if it's a Microsoft operating system, then this will not apply to any Linux operating system or Apple operating systems, okay? I don't know, I don't think so, actually. I don't know what they do if they don't have a DHCP server. I don't use Apple at all. I've used Linux, but generally I've used them as servers, so they've got static IP addresses. Or I've used them to get an IP address from DHCP server. I've never actually experimented with the fact that what if they didn't have a DHCP server. So if anyone else does, Harrison, have you used Linux yourself?
Yeah.
What happens if they don't? If it doesn't have a DHCP server?
You have to set one statically, or
yeah. Yeah. So basically, that's what we're asking about. Does it have anything in place like a PIPA? I don't think so, because this is a Microsoft thing. Okay. So you've just confirmed it. That's good. Okay. Let's move on. Of our IPv4s, there's different classes. Okay, so if you look at class A, that is /8 is that notation, isn't it? See, CIDR, it's called CIDR notation. /8. So /8 means it's going to have a subnet mask with 8 bits as ones. So it's 255.0.0.0. So class A IP addresses are in range of 0 to 127, basically. Okay, so if I see an IP address which is starts with any number between 0 and 127, I'm going to know that's class A. Okay, I'm just going to know. And you're probably wondering, do we need to know that? Yes, because then you should know, based on that, what kind of subnet mask should it have by default. Okay, so class B goes to the next level, goes 128 to 191, and all the way to 255 here. So it's anything that starts with 128 or up to 191, then I know it's a class B. And then if we look at class C, it's going to be 192 to 223. So anything that starts with 192 to 223, I'm going to know it's class B. Those are the only three classes you need to know about. Okay, so there's class E, which is really for experimental and no one uses it, and there's a multicast area as well, which is what's it? I don't know what that's saying. There's a multicast area as well, which starts with 224. But these three are what you need to know. And you're probably going, am I supposed to remember those ranges? Sort of. You don't need to remember the last one, but you can just remember the next one. Okay, so anything that starts with anything under 128 is going to be class A. Anything that starts above 128 or below 192 is going to be class B. And class C is anything that's below above 192 but below 224 is going to be class C. That's the easiest way to remember. Okay, I'm sure you don't want to know the mathematical way or how to do this, but let me just show you anyway. But if you can remember just by doing whatever. Okay, let's actually clear this out. Let me just show you. Let's get rid of that. Class A. It's the position of the 1. Okay. If class A, let me just copy this again. So class B, and oh, I can't spell obviously, and Excel doesn't have this auto spell checking. Class C is the position of this 1. Okay, or actually it's the position of the 0. I got myself mixed up. It's the position of the 0. And basically this 0, as you can see, moves just one spot for each of the different classes. All right, let's work out what that means. All right, so basically, sorry. So it's a position of the 0, but these ones, once the 0 moves, these become 1s. Okay. So if these are set in stone, so what is the minimum? The minimum is basically when all of these are equal to 0, aren't they? Oops, sorry, delete. The minimum is when they're all equal to 0, 0, 0, 0, which gives us 0, 0, 0, 0. So we're looking at just the first octet, okay? This is the one that we're interested in for the classes. So that's equal to this. When it's all 0, that's the minimum. And what's the maximum? Maximum is when instead of being all 0s, they're all 1s. And 0s is easy to work out. When they're all 0s, it's 0. But when they're all 1s, if we add this up, it's going to be 64 plus 32 plus 16 plus 8 plus 2 plus, plus 4 plus 2 plus 1. It's going to be 127. And so the range is okay, between that, if we're looking at this first octet. You get me, guys? So again, if we look at this, the next range is going to be 0 when the minimum number is where it's all zeros, and that is going to be 128, isn't it? So if we're looking at, again, this first octet. So the first and the maximum number is where these zeros are all ones. Oh, sorry, yep. And if we add that up, it's going to be 128 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. And I feel that if we get our calculator out and add it all up, so actually I probably don't need it. 128 plus 32 is 160, plus 16 is 176, plus 8 is 184, plus 4 is 188, plus 2 is 190, plus 1 is 191. All right. And if we're again looking at that first octet. So now if we go look at that, again, class C, if we had these as all zeros, again, if we add this up, it's 128 plus 64 is 192. It's the minimum. And the maximum is where these ones are ones. And basically that is 128 plus 64 is 192. Plus 16 is 208. Plus 8 is 216. 220. 222, 223. And if we're just looking at these first octet. So it's not random, okay? These numbers are not random. So 0 to 127, 128 to 191, 192 to 223, they're not random. You see how that matches up pretty well to these numbers here I showed you? They're not random because nothing in IT, in maths, is random. It's by design. And that's how they've designated these ranges. So what's the net effect, really? Net effect is that if it's class A, it's going to have a one octet of for the subnet mask. Class B is going to have 2 octets of subnet mask, and for the class C is going to have 3 octets for the subnet mask. You get me, guys? So what does it really mean effectively? Effectively, so this is annoying me, so bear with me. This thing is annoying me a little bit, so because that's not meant to be. This is not. This is annoying me. This is not meant to be dash. It's meant to be D, and I think that's meant to be 224 dot something dot something. I think it's slash something, but it's going there, but I can't remember exactly. So it's by design. So basically, if we talk about this, we're only going to concentrate on class A, B, C, because they're the ones. Class A, B, C. They're the only ones that's being used for our networking computers, Okay, like I said, there's multicast, which is class D, and experimental, which is class E. But what the net result is, if we have a small subnet mask number, 8 bits, we're going to have a large networks, small number of networks. So there's only 128 networks, but each network can fit 16 million IP addresses. Too big, isn't it? Okay, but possibly required by someone. Class B is sort of in the middle. You're going to have 16,000 possible networks, and each network is going to have 65,000 hosts. Still quite big. And Class C is going to have 2 million something possible networks, but each network can only be 254 bit. What's a 254 hosts? So you can see that you can have lots of networks, but lots of small networks, Class C. Lots of hosts, but only a few networks, about 50-50. So that's what we are talking about. All right. So let me. All right. So segmentation. So let's talk about this network here. You can see this is a switch as a router connected to a switch, then which is connected to multiple other switches. So basically what you're going to end up is if each one of these switches 48 ports, you're going to end up with 4 times 48, 96, 192 computers on this network. It's the same physical network. And if one of the 192 computers sends a broadcast, it's going to go into this switch. It's going to come out every port of that switch, inclusive of these ports, which is going to this switch. It's going to go out every port inclusive of these ports, and then it's going to every computer on the whole network. So the chances of one computer sending a broadcast is pretty low, but the chances of a computer sending a broadcast out of 192 is very high, isn't it? It's just like the odds. So therefore, if every computer on the whole network is going to stop at that point because someone's sending a broadcast, you can see how that's a bit of a waste of time, isn't it? So therefore, many protocols use broadcasts such as ARP to locate other devices, or host and DHCP discovery protocols to find the DHCP server. Switches propagate broadcasts because that's its job. It doesn't know who's it for. It's for everyone. So it's going to send it out of all the interfaces except for the one that received it on, obviously. And the only device that stops a broadcast is the router. The router will not send the broadcast anywhere else, because the broadcast is only on the local area network. And this is what's called a broadcast domain. Each router interface connects to a different network and also a different broadcast domain, and broadcasts are only propagated within that broadcast domain. So obviously, if there's too many broadcasts, too big, it's going to cause problems. It's going to waste processing power. It's going to waste network bandwidth. So the problem with large broadcast domains is that hosts can generate excessive broadcasts and negatively affect the network. So 400 users in this case. It's a class, I can see that's a class B, and I can see that's a private IP address range just by looking at it. So that's what I want you to be able to get to. Okay, can you see that? It's a class B because it fits into that area here, doesn't it? Do you see it's a private because it fits into that format here, doesn't it? So that's why I can pick that out straight away. And basically, in my mind, there's a couple of things already triggering. So that's a private, that's a class B. That means it's going to be a /16, which is going to give me a 255.255.0.0 mask, which means the first 2 octets are network and the last 2 octets are host. You see how just from recognizing that, I can get all that information in my head straight away. So it's useful for not just being a nerd and working out these numbers. It's also useful because now I know that, hey, this is going to mean that if I see something that's not what I'm expecting, that when I've just lined it up, if someone's saying, hey, the router's not routing my IP address, then I can say, that's because you're private. Or, hey, this other guy who's on 192.168, I can't ping him. Well, he has to go for a router. Do you have a router? Okay, and stuff like that. So that's what I want you guys to almost get to, because it's actually very helpful when you're troubleshooting to understand what should be versus what you're seeing. All right, so if this has got 400 users, then that's fine. That's got a large broadcast domain. Obviously, the solution is to just segment it, cut it up. You notice that, hey, it's the same IP address, but now I've actually changed the subnet mask, haven't I? From 16 to 24. Which now, if you notice that, well, I noticed that's class B. Why is it having a class C subnet mask? Because we can. Those classes are just what's default default, but we can do what's called subnetting, and that's what we're trying to get you to actually cut that larger network up into smaller networks. And that's the hard part. That's the hard part. And you're probably going, oh, there's so many hard parts. Why is that the hard part? Okay, so basically we've done that. Now the first 3 octets, so /24 means 24 bits. 8 plus 8 plus 8 is 24. So the first 24 bits is the 255, and the last one is 0. So the first 3 octets are network, and the last octet is host now. So basically what this person's done is just split this network into 2 by having 200 hosts on each one, and I've reduced the broadcast domain by half. Okay, that's one reason of reducing the split network segregation. Other reasons for segregation is that, hey, what if they're physically located on different floors? In this case, location, physically located in different areas. What's the point of making one large network where you can just have lots of smaller networks? Okay, so for example, you wouldn't expect this room's network network to be the same as the room that's in the library, would you? Because it's totally in a geographical different area, and we've got limitations of cable length and all that kind of stuff. So it's probably better off if we have different physical networks. It could also be different functional groups. So for example, here we might have, this looks like something like TAFE, we would do at TAFE. We might have a student network, and we might have various staff networks. Okay, why do we want to do this? We basically keep the traffic for the students on the student network, and accounting, in this case, accounting traffic on the accounting network, and so forth. And this is also for security, isn't it? So if the student tries to access the administration LAN to try to hack the enrollments database to change their results, for example, we could have rules here on this router that can control what kind of access, or what, if any, that these computers can have to other networks. If you notice that, if we look at this IP address, you might notice that that's a 10 network. That's a Class A, isn't it? And that's private also. But now it's got a Class C subnet mask, or 24-bit subnet mask. Again, that's been subnetted. We could also separate the network based on the different types of devices. For example, there'd be a printer network, a computer network, and a server network, because we might have different rules about different networks. So all of this is actually bringing us to actually subnetting a network to be smaller networks, which what they've already sort of done. So /8, this is a CIDR notation, basically represents a subnet mask as 255.0.0.0. /16 is 255.0.0. /24 is 255.255.0.0. 8 bits, 2 lots of 8, 16 bits, 3 lots of 8, 24 bits, hence those numbers. And what does it look like? If you want to think of this is the IP address, this is the subnet mask. If you want to think about it, these first 8 bits in the IP address, the first octet, they're all ends, or network bits. And all of these other ones, which are across the third, these other octets, these are H's, or host bits. So if we have a small amount of numbers to represent the number, the different networks, we can only have a fewer networks. But if we have this large number of host bits, we can represent lots and lots of different hosts. That's why we can have 16 million hosts here. And this is sort of middle ground, half, about 65,000 hosts. And this one, it's a large number of different networks, but each network only can have a small amount of hosts. Subnets on boundaries. So boundaries is where those dots are. So subnetting on boundaries is really easy. We just substitute whatever subnet mask that you meant to have with a different subnet mask, which is still like 8, 16, or 24, and then we just turn it into effectively a Class C network. So this is a Class A, but if we slash make it with /26/16, we are effectively saying the first 2 octets are network and the last 2 octets are host. And we can take the same network and we put a /24 on it, and we can say the first 3 octets are network and the last octet is host, giving us almost effectively what we normally use for a Class C. Is that okay? All right. So segmenting on boundaries, which is basically where the subnet's mask uses up all the bits in a particular octet. So /16 means you're using the first 2 octets fully for the subnet mask, and /24 means you're using the first 3 octets fully as a subnet mask. But the tricky part is, what if it's not on the boundaries? Remember, the boundaries are /8, /16, /24. 8, 16, 24. Oh, look at these. We've got /25, /26, and /27, and so forth. So they're sort of weird, aren't they? So that's what we're going to come back in the next lesson and continue on with. Okay, so just be proud of yourself in this lesson that you've hopefully understood how to do binary decimal conversion, and you've understood that some definitions about IP addresses and how the different classes are. Some are private, some are public, some are PIPA, some are loopback. And we understand how the subnet mask changes where the host and where the network portions are of our IP address. So be happy with that. But it's about 11 o'clock. Let's go for a break. I think all our brains probably need a break. And when we come back, it's going to be even more hectic.